Okay, here's today's molecule. It's vanillin. Probably not a big surprise to find that it's the main flavor component of vanilla. No way. So natural vanilla extract is like 90, 95, 97, I don't know, something like that percent vanillin. And then the rest of it is a huge range of other compounds, probably hundreds or thousands, that give real vanilla, like the real vanilla flavor. But when you artificially flavor something with vanilla, you're just adding, usually just adding vanilla. And so the reason that, and this is really the case for basically all artificial flavorings, is the reason that they taste just a little bit off is because you're getting like 99.9% of the flavor, but there's just a little bit of hundreds or thousands of different other compounds that give it the natural flavor, if you will. So, but there's vanillin. It smells like vanilla, tastes like vanilla. We'll use it at the end of the semester, and it's a very nice lab because the whole room smells like vanilla. So you should be able to label 3 or 4 functional groups in this molecule. So there's 3 oxygens, 3 heteroatoms, and those are each part of a functional group. There's also this 6-membered ring with the double bonds in it. So that is a benzene or aromatic ring. Technically, it's not a phenyl group because a phenyl group is only attached at one position to the rest of the molecule. But if you said phenyl, that's okay for now. We have this OH, which is called what? Hydroxyl or alcohol. What about this one? So if this one stumps you a little bit, it's an oxygen with 2 carbon-based groups attached to it on either side. So that's an ether. And then this guy, what's that? There's a broad name. Yeah, so the general name for any CO double bonded functional group is a carbonyl, but specifically what kind of carbonyl is it? It's not a ketone. A ketone would have an R group on both sides, but because this one has a hydrogen, yeah, it's an aldehyde. Okay. Okay, so we've spent all this time talking about drawing. And at this point, we're basically done with the drawing part. Although there's certainly going to be a lot more drawing that you'll have to do. But as far as new stuff for drawing goes, we're about done with that. But now we need to be able to give names to the molecules that we're drawing. Now, the functional group names is a significant sort of step toward that. But we need to have a way to describe a molecule with no confusion as to what we're talking about. So I could say that that molecule is an alcohol, which is true because it has an alcohol group. So we could say that the molecule itself is an alcohol, but obviously there's a lot of different alcohols. So we need to have a specific way to talk about these things. First, we're going to have a little bit of a side note kind of thing because we have to talk about the different kinds of bonds that we see in organic chemistry. So you probably have seen these in general chemistry. So we have sigma bonds and pi bonds. So let's say that we are talking about a carbon-carbon bond in both of these cases. In a sigma bond, we have the two orbitals overlapping head-on like this. So the way I've drawn them here, they're sort of like sp3 orbitals, but the two big lobes of the orbitals are pointing toward each other. And so that's the area of the molecule where the actual bond, the bond forces are going on, is between the two atoms. That might seem obvious, but there's a contrast between that and pi bonds, where we're using the orbitals that are perpendicular to the bond. And the overlap that's making the pi bond is side to side. All right. So we have sigma bonds and pi bonds, but we also have, right, we have single bonds, double bonds, and triple bonds. How do those relate to sigma and pi? Okay, so being careful with my handwriting here, number of sigma and number of pi bonds in a single, double, or triple bond. So the rule here is that the first bond is always a sigma bond. And any additional bonds on top of that first sigma bond are pi bonds. So all bonds, single, double, or triple, or quadruple, if you like, in inorganic chemistry, have one sigma bond. So in that case, how many pi bonds are in a single bond?
You have one, a double bond, between a triple bond, and zero and a single bond.
Right. So the single bond, well, it's just the sigma bond, so no pi bonds. The double bond, the first, and it didn't really matter which of the two bonds, because it's just a diagram, and this is not reality. But the first bond of the double bond is a sigma bond, and then the other one is a pi bond. And then we can extend that to the triple bond case. The first bond is a sigma bond, and then we have two pi bonds. So make sure you can identify either in, a form like this or in a molecule if we have a single, double, and triple bond, but maybe more importantly, if we have pi bonds involved. Sigma bonds are less interesting because there's always a sigma bond and there's always one of them. But when you have multiple bonds, the extra bonds are pi bonds. Okay, so that's our little side note on sigma and pi bonds. So going back to naming of molecules, we have a couple definitions here. A hydrocarbon, it's kind of, well, it is what it says on the tin. It's something with only carbon and hydrogen, hydrocarbon. No oxygen, no nitrogen, no heteroatoms. That's sort of an alternate definition, is a molecule with no heteroatoms. Also, we need the term saturated. And saturated means that we only have single bonds, aka only sigma bonds. Okay, so first molecule, is that a hydrocarbon? Yes or no? Yeah, first one is a hydrocarbon because it's only got carbon and hydrogen. The nice thing about that is it's super easy to see instantly as you look at the structure. No oxygen, no letters of any kind. So it's a hydrocarbon. Okay. Is it saturated?
Uh,
Yep.
no, like the double one that like why is
No, there's no double bonds here, just single bonds. So we've got only single bonds and it's a hydrocarbon. So this is a saturated hydrocarbon. And that's what an alkane is. It's just a saturated hydrocarbon. Okay, our second molecule, that's also a hydrocarbon because we don't have any letters of any sort. Is it saturated or unsaturated? Yeah, unsaturated. We've got a double bond there. And this specific molecule is a type of alkene, but there's a wide variety of different unsaturated hydrocarbons, so we can't just give them one name. By the way, saturated and unsaturated, that's the same as saturated and unsaturated fats. So the reason that unsaturated fats generally are less good for you is because that double bond is more chemically reactive, and so it can do bad stuff in your body, I guess. I don't know. I'm not a biochemist, but so that's what it means when you're talking about those two different kinds of fats. What we're going to focus on here is saturated hydrocarbons and hydrocarbons with, well, if it's got one or two heteroatoms on it, it's not a hydrocarbon, but uh, hydrocarbons that are, slightly substituted with other things, in this case, halogens. But mostly we're going to talk about naming of alkanes. And the naming really of all chemicals, but in our case, alkanes. Is standardized by the International Union of Pure and Applied Chemistry, IUPAC. And these are very systematic names. They're systematically generated. And so we're going to learn how to do that. You can basically just being a robot. Um, and these names are useful in that you can come up with exactly one name for any chemical, and it unambiguously identifies that chemical and there's only one correct answer. But of course, in practice, we use nicknames. We use sometimes IUPAC-ish names that are actually wrong, but we use for one substance, which is annoying, but is it's kind of the way that it is sometimes. But we can come up with standard names for any organic compound. So this is one thing that's used even not in usual IUPAC names, and that is that alkanes always end in ane, alkane. So that's where the ane suffix comes from. Methane, butane, etc. Okay. This is going to be a 3 across by 10 down table, so make sure you give yourself some vertical space here. So this is going to be the names for the first 10 straight chain alkanes. So just a chain of carbon atoms completely saturated with hydrogens. That's what we call it when we don't have any heteroatoms or any double bonds. Well, heteroatoms are okay, but we don't have double or triple bonds, right? We call that saturated. So carbons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you will have to remember these. Fortunately, it's only the first four that are weird, and the rest of them come from, or like the standard Greek or Latin prefixes that we're used to. So one is meth. And yes, the meth of methamphetamine, that's that meth. Two is eth. So that gives us ethane. Three is prop. So what's that alkane? Propane. Yeah. Four is bute. That gives us butane. And then the rest are sort of standard. Pent, hex, not sex, hept, not sept, oct, non. I mean, I imagine the first four come from Greek or Latin in some regard, but they're maybe not the ones that you're used to seeing. So pentane, hexane, heptane, octane, nonane, and decane. These continue, of course, but generally you kind of see up to 7 and 8, and that's about it. If you need a mnemonic for the first four, there you go. I'm never going to be able to forget that one. So, okay. So those are for just the regular straight chain alkanes with no branches, no nothing else. Of course, we're still going to use these to name other alkanes, but we got to have some sort of backbone to start with. So another definition, substituent, and a substituent is just a branch off of the main chain. So we have that straight chain alkane of 1, 2, 3, 4, 5, 6, 7 carbons. So that is what? Heptane. And we have heptane with a substituent of some kind. So what we're going to do is use heptane as our sort of base name. And then in front of it or before it, we're going to add all of the information that tells us about what the substituents are and where they are. Okay. So here is, sorry. Sort of the cheat sheet for naming of alkanes. First step, which we've already done, is to identify the parent chain. So in this case, it's easy, right? It's horizontal and it's a nice long parent chain. But we're going to see that sometimes it's not always drawn horizontally. And there may be some question as to what if the parent chain is the longest one or if it's not the longest one. Generally speaking, unless there's some sort of heteroatom, the longest chain is going to be the parent chain, the longest continuous chain of carbons. So we need to figure out the parent chain. Then figure out what our substituents are. Then we need to number the parent chain, and we'll talk about exactly how to do that, and assign a locant, kind of like an address, to each of our substituents. Our substituents go in alphabetical order.
Wait, is that locants?
Yeah. LOCANTS, locants. And then so we'll alphabetize these substituents just to make it clean and neat. And then we construct the name based on the rules that we'll talk about in a second. So that's sort of your 4-step guide for naming of really all molecules, but we're only going to talk about hydrocarbons and some alkyl halides today. And then further down the road, as we get to different functional groups and talk about their specific reactivity, we will mention some naming conventions for those specific functional groups. They tend not to be horribly different. Okay, so let's actually name this molecule. Okay, so the parent chain, we already did that. Seven carbons, so that's heptane. And that's the longest continuous chain of carbon atoms. We kind of need that. Okay, second, we need to identify and name our substituents. So obviously this group hanging down there is a substituent because it's not part of those 7 carbons that make up the chain. What's the name of that substituent? So be careful that this carbon here is already part of the parent chain. And so there's only one carbon there that's not in the parent chain, so that's methyl. Only have one substituent, so just one methyl group. Methyl because it has one carbon and it's just a CH3 group. And if we look at our, it didn't matter if it's on the bottom or not, but okay. So our next step is to do numbering. So we need to number the parent chain. Just the parent chain is going to get numbered. The rule here is we want to make the lowest substituent number as low as possible. So we're going to number the chain 1 through 7. And we want the substituent, the methyl group in gold, to be on the lowest possible number. So clearly we're going to start from the right-hand side. 1, 2, 3, 4, 5, 6, 7. So now we can see they can hear you just fine. We can see that the methyl group is on carbon 3. So I'll add that here, methyl on C3. And finally, we just have to construct our name. So I'm going to do it first and then explain how to do it. This is going to be 3-methyl heptane. So rules for making those names. We don't use any spaces. So there's no space between the L of methyl and the H of heptane. Okay. We put a dash in between the locate number and the substituent name. And so actually you can extend that rule and say you're always going to put a dash between any number and any letter in an IUPAC name. And we also don't capitalize anything because these are common nouns, not proper nouns. So those aren't the only rules for constructing names, but we're going to go through a whole bunch of examples that have different weird things going on. And through those examples, I think we'll hit all of the different rules. Okay, questions on how I got 3-methylheptane from that molecule?
So you got the three, then the fact that the constituents on the third carbon on the right side.
Correct.
You got the methyl because there's only a single constituent. You got the heptane because there's 7 total carbon bonds in the chain, right?
Correct, except for the methyl is methyl because that substituent there only has one carbon. Now, if there's multiple substituents, we're gonna do that. In fact, well, not quite next, but in a few examples, we'll do multiple substituents, and that just extends the name a little bit more. There's another thing I was gonna say. I forgot. Okay. All right. So now let's look at some issues that can and will arise when you're doing these names. So what about this? Okay. How many carbons are in the longest chain here? 7. Okay. So if we try and just do the horizontal chain like this, we get 5. But the parent chain is always the longest chain, except for the exceptions, which we'll get to later. But if we're looking for the longest chain, we can't go that way. We have to go up and around instead to get a higher number, which is 7. Okay, so what's the parent name for this? Yep. Heptane again. Okay, now we need to number our chain, and we want the substituent to be on the lowest number possible. So, well, we can't start in the middle. We got to start at one of the ends. Oh, it is in the, yes, yes, good. Yeah, it's in the middle. Yep. So I went from the left, but you can also go from the right. In either case, you're going to get that our substituent is on carbon number 4. And that substituent here is also methyl again. So we have a methyl on carbon 4. And so we have now 4 methyl heptane. One, two, three. Oh, that's where I messed up on my notes. All right. Okay. So what's our parent name for this one? Octane. In this case, the parent chain is horizontal, although there's 2 CH3 groups here, so you could say that the parent chain continues horizontally, which is what I would do, or you could say that it goes down. Doesn't really matter. We have an octane. Okay, what about our substituents? We have 2 different kinds of substituents. One of them is a methyl group. What's the other one? Yep, ethyl. Okay, for our numbering, should we start on the left or the right? Yep, the right, definitely. That's what I did in my notes. Made that mistake. 5, 6, 7, 8. Okay, so we have a methyl group on methyl on C4. Okay, so now we have 2 substituents. So we're going to have to alphabetize them in order to construct our name. So if you have to sing your ABCs, that's okay. But hopefully, by doing that, you can see that ethyl is before methyl in the alphabet, even though methyl is a smaller group. So you might think, oh, less carbons, it should come first. I don't know. That's just what I think, but who cares what I think? So ethyl coming first in the alphabet is going to come first. Okay. So this becomes 4 ethyl. And then we need to separate the next locant, which is going to be the 2 from methyl with dashes. So 4-ethyl dash 2 dash methyl octane. 4-ethyl 2-methyl octane. So anywhere we have a number and a letter next to each other, we need a dash. Okay, our parent chain for this is 6. So it's a hexane. We have 2 substituents that are the same, right? We have 2 methyl groups. So that's okay. We have a way to handle that. 2 methyl groups. And like our example from a little bit previously, the numbering here doesn't matter because if you go from both ends, you'll have one of the groups on carbon 3 and one of the groups on carbon 4. So we have a methyl on C3 and a methyl on C4. Now, to indicate that we have 2 methyl groups, and this is kind of redundant.
Left technically because you have one. Oh no, yeah, just saying. Never mind.
Yep, same either way. So because we have 2 methyl groups, we have to use a prefix to show there's 2, and that's going to be di, tri. 4 is tetra, but we probably won't see 4. So this is redundant because we have to include both of the locants, 3 and 4, and that implies that we have 2, but again, them's the rules. So the way we do this is 3 comma 4 with no space in between dash dimethyl hexane. Are we happy with that so far? Cool.
Yeah.
You can see why people get tired of this really fast. Because, I mean, it's not hard, it's just really tedious. And as soon as the molecule gets bigger, like at this point, the name is already just as long as the structure. So, yeah. All right. Uh-oh, a ring. What are we going to do? All right. So, turns out this is fairly easy as well. And that is, we just include the cyclo prefix in front of our parent chain. So in this case, when we have a ring, the parent chain is always going to be the ring. Again, there's exceptions to this, but for our purposes, the ring is always going to be the parent chain. And so this is a ring of 6 carbons. Again, practice your hexagon drawing skills. And so this is not just a hexane, but cyclohexane. Cyclo circle. Okay, and we have one substituent, and that's again a methyl group. Now, for numbering, well, we can't start at the ends because it's a circle. Circle doesn't have ends. And so we're just going to put the substituent on the lowest possible number. So this is going to be carbon 1. And I mean, at this point, it doesn't matter what the other numbers are, but we can go around in either direction as we like. I'll go clockwise. And if there were multiple substituents, you would need to figure out which direction puts the things generally on the lowest numbers. Okay, methyl on carbon 1. And so this becomes one methyl cyclohexane. Or a lot of times, because the number 1 in this case is redundant, because if we just have methyl cyclohexane, well, there's just one group somewhere on the cyclohexane, so the number doesn't matter. And so sometimes we'll just leave it off. The only thing I would caution you is it's better to have more information than less. So if you're not sure whether you can get rid of the number, just leave the number there. By the way, little trick for drawing these straight chains. Okay, so this is going to give away how many carbons are in the chain, but I think that's okay. I want nonane, so I want 9 carbons. I think the way that I do it is I count the number of lines rather than the number of carbons. Okay, so if I want 9 carbons, that's going to be 8 lines. Or what I do is I count the number of lines starting at 2. Okay. So this is going to be hard to do because there's a lag, but essentially I go 2, 3, 4, 5, 6, 7, 8, 9. I don't know. It works for me. If it works for you, that's great. Of course, always check your, oh, sorry, we need the substituents here, sorry. Duh, like so. Okay. Okay, I think it's pretty obvious from this that we need to start numbering on the left. I know I'm going a little bit out of order with the steps that I told you to do, but that's okay. We can number first and then look at substituents later. Okay, so our substituents, we have 3 of them. In this case, we have a methyl on carbon 2. We have a methyl on carbon 3. And we have an ethyl with an E on carbon 5. Okay, if you're particularly astute, you will have noticed that we have a dimethyl and an ethyl. Okay, so now how do we alphabetize? See, this is so anal of them to be this precise about how I have to do it, but okay, do we alphabetize the E first and then the M for methyl? Or do we do D in di comes before E for And the answer is we just use the plain substituent name without the di or tri, whatever on it. So ethyl is still going to come before dimethyl. All right. So, sorry, we have 5-ethyl dash 2 comma 3 dash dimethyl nonane. Yeah, there we go. 5-ethyl 2,3 dimethyl nonane, right? Did I do it right? I think I did. Yep. Okay. Couple things to notice about this molecule. First of all, we have 3 methyl groups. So we're going to need a tri prefix. Okay. But additionally, and this is something that that based on the rules, you should already know this, but it's good to remind people of this, is we're looking to minimize the lowest locant number. Okay. So you might initially look at this. Initially, I need to eat lunch. You might look at this and say, okay, well, most of the substituents are on the left, kind of, so we should probably start on the left side, right? And that would give us 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, this is octane. That's not up for debate. So that puts our lowest locant number at 3. I shouldn't have done that because I'm going to undo my stuff. All right. But that's not correct in this case because we can go the other direction. 1, 2. And we can get that substituent on a 2. And that is the best thing in this case. We're not looking for some people, I hesitate to say this because I don't want to put this in your brain, but some people think that it's like the lowest sum of the locant numbers. It's I thought that even. That was a rumor that went around at my undergrad. That's not true. Lowest, minimize the lowest locant number, screw the sum or any other substituents. Okay. All right, so this is octane. Actually, go ahead. Finish the rest of it on your paper. Hopefully you got 2,5,6 trimethyl octane. Questions so far? Cool. Okay, this is where we finished in Bluffton, and so y'all are fast. And so I'm gonna actually wait to continue the next stuff until next time. What I will say on the homework is I think there's a couple on the homework that have halogens on them. On Blackboard. I almost said Canvas on Blackboard. Um, If you see one with halogens, we haven't talked about that yet. We'll do that next time. Um, if you want, let's do office hours in here until I don't know 2:15 or so. Um, unless you need to stay later for some reason, and then just let me know. Okay. Thank you.